Again, this talk is about a novel soft growing robot and thinking about the human interface to that. In order to describe this, I'll have to talk quite a bit about the soft growing robot and its properties, but I will be discussing more towards the end what are the human interface techniques we've used, what we can draw in terms of knowledge from other types of robots and shared autonomy with them, and then present some, I think, interesting open questions for the field that I hope we can discuss during Q&A. So first of all, the type of soft robots that I want to focus in on are in this class of continuum type robots, as well as robots that effectively grow. So these are a class of robots that have this long, thin form factor that are highly flexible. Sometimes they are stretchable, but sometimes they don't stretch and they merely flex, which can be an important property for controlling them. And we're in particular interested in how we would use these for manipulation. On the growing side, I would say that there's been very little work done in robots that grow. Some of them expand, but maybe don't actually grow. In this case, there's really one other group that's, well, actually, there may be two other groups now that we're aware of that are deeply working on this. Really, one of the pioneers came from Barbara Mazelai's group, where they have actually been 3D printing additional material on the end of the robot in order to grow it. And as you'll see shortly, our mechanism is quite different, and similar mechanisms to ours are now being used also by Caspar Altefer's group. So in this class of robots, we have a subset of soft growing robots where we use basically an inflated plastic bag. And if you imagine this in a tubular form factor, if you took that tube and you stuff it inside of itself and then pressurize from the inside, the material inside comes out of the tip through a process called eversion. And this is reversible, as you can see hopefully in the video in the left. If you pull on the material on the inside, it will invert into the tip and retract. And if you apply pressure from the inside, then it everts and it grows. And because the way in which this robot is steered and controlled is very important to how we would think a human should interact with this and how you accomplish shared autonomy, I'll be talking in some detail about the different types of steering techniques available, and we can think about does shared autonomy make sense with these various steering techniques. As you can imagine, this method has a lot of advantages in terms of a potential manipulator because it doesn't actually have friction with respect to the environment when it grows. Imagine in a medical application, a catheter that has to push against the walls of the tissue in order to be inserted. When you grow out of the tip, you remove that friction. In addition, it has a much smaller body workspace that we'll discuss a little bit later. So our long-term vision for this project, what we're trying to achieve, and the reason that we think we need soft autonomy with this type of robot is that we would like to have robot manipulators integrated into human environments. So first of all, the soft-growing robot itself has advantages for this. The soft-growing robot is probably not likely to injure the human. I think we can't always go with the assumption that soft robots are safe around people. We've had pneumatic devices explode in the lab somewhat dramatically. But what you can imagine is it has a much lower effective inertia as it moves around a workspace, and therefore is unlikely to cause damage to a human by collisions. In addition, it can bend and curve into spaces that other traditional rigid manipulators are unlikely to be able to reach. The shared autonomy aspect comes in that we imagine a scenario where someone is in their home environment, for example, in aging in place, or an older person who can't accomplish all the normal activities of daily living on their own, requires some assistance. But to avoid, for example, living in a nursing home or an assisted living facility, which today in the age of the global pandemic, we would like to avoid people living in large, close medical situations close to each other. And the idea is we would like to assist such individuals from a remote location. So as pictured on this slide, you can imagine a person in a different location effectively teleoperating this robot to assist a person who's in their home. And that teleoperator could be a caregiver. It could be a hired person. For example, instead of having someone come in to clean the house, they could remotely teleoperate this robot to assist in cleaning. And it could also be a family member or a friend, and the robot could even purposely physically interact with the human in their environment in order to play games or provide other social, emotional support. So all of these scenarios, while potentially could be accomplished using direct teleoperation, I think especially when you have a robot with this strange form factor that doesn't really kinematically match what the human body can do. It can move around 3D space in the same way the human arm is, but this gross degree of freedom is quite different from the human kinematics. So what we would like to think about is what are the ways in which you can have shared autonomy. One definition being that the robot is partially autonomous but has some human in the loop control, or that the two people, the remote person and the local person, are sort of sharing in this autonomous robot behaviors. So in that context, direct teleoperation of the robot is probably not what we want. And what we're doing in this larger project is thinking about the role of shared autonomy in these kinds of scenarios. So big picture, our project goals and this ongoing research effort in our lab is to design and control soft manipulators. And I'll be talking about that design and control first. And then the other is to create useful haptic feedback or guidance modes or shared autonomy that functions across a wide spectrum of possible human-in-the-loop operation modes. So one of the challenges in thinking about shared autonomy for such a system is what are the natural behaviors of the robot? What is it capable of? And in fact, for this type of robot, we have a lot of choices for how we steer it and what those degrees of freedom look like. And that very much impacts what kind of shared autonomy we have. So I'm going to be asking this question over and over and giving some different answers for how you steer this type of robot. And we can think about for each one, is there any way in which shared autonomy or human in the loop control makes sense? Oh, sorry, my sound. I don't know if you can hear that, and I apologize if you're hearing all the sound of the pneumatics from these different scenarios. But the idea here is that one way to steer a soft-growing robot is not to steer it. I'm going to see if I can pause this for a minute because that was at least loud on my side. And so in all those examples I was just showing, these were cases where the robot really wasn't steered at all. It just had certain properties like floating on water or popping through small holes that were useful. And all of those capabilities are surrounding the passive mechanics, the advantageous passive mechanics of this type of robot. And really, this is overall a major motivation for soft robotics, is that they comply to their environment and have these passive mechanical effects. Some people refer to it as an embodied intelligence, which sort of negates the need for any sort of active control. So when we take advantage of those properties, my point is that we don't need shared autonomy. There's no control anyways, so there's really no human in the loop aspects. But of course, there are other ways to steer it, which may be more important. So another way is to pre-form the robot, which is to design the robot to have some pre-bent locations such that when it grows into an advantageous shape. And again, because I didn't expect the sound to be playing, I'm going to pause at least what I think is the most noisy video. So in these preformed robots, when it comes to the live interaction with the robot in teleoperation, once the robot has been created, there is not much use for shared autonomy. However, I think there's a real potential here for the human to have interaction with the soft robot in the design process. So one of the things that we're doing is thinking about virtual reality scenarios where a human can be in the loop in the design process of the soft robot, and you sort of have a shared autonomy in that design phase where the design can take, the design process takes advantage of our understanding of the kinematics of the robot and its constraints, and there's a sort of autonomous optimization that happens in order to design the shape of the robot. And in the meantime, the human can bring in their intelligence to identify different desired behaviors or access points for that robot. And this is something that we've actually already achieved with a very different kind of robot, a concentric tube robot. In that case, having for a clinical application, a surgeon in the loop design process where the surgeon helps design the robot in a virtual environment, which also has some autonomy in optimizing the design. And we believe this kind of human in the loop design process is a form of shared autonomy that could be used in order to create preformed bind robots, which have advantages in terms of their simplicity, but disadvantages in terms of their inability to react or change their shape in response to changing environmental conditions. I'll also note that for this very simple type of preformed vine robot, we actually have design and assembly instructions publicly available at vinerobots.org. So if anyone is interested in trying their hand at building such a strange robot, you're welcome to do so. All right, now we'll get into maybe some more controllable and interactive types of steering a robot. So I'm gonna play these videos for a minute. These ones are not too noisy, great. So this is another example where we actually use the environment to help steer the robot. So in this case, we have growing robots that are partially preformed in some cases, but also just push on the environment in order to steer themselves. And in this case, a human in the loop could be very advantageous in terms of selecting the way in which the robot interacts with the environment in order to push the robot in one direction or the other, such that you get the desired steering behavior. So you can imagine a two-layered form of shared autonomy here. Because the robot can be somewhat preformed, you could have the human be involved in a shared autonomy process that's in the design phase. And then when it comes to actual deployment of the robot in a novel environment, which may differ somewhat from the environment where the robot was designed, went through this design planning process, the human could help steer it in ways that interact with the environment. And here it's very important to have models, as shown on the left video, of what sort of interactions with the environment and how those could happen and how those would result in different paths of the robot. This may be less applicable in manipulation tasks, which are more likely to occur in open environments. But in navigation tasks, this is a place where shared autonomy could be extremely useful. All right, let's go even more active into steering. The next is the idea that you really change on the fly the local curvature of the robot. And this is one of the first ways that we did that in an active way, depending on feedback control from a video camera mounted at the tip of the robot. So in this case, we lengthen material on part of the robot, and that effectively causes a turn. And what's shown on the right is actually a completely autonomous version of the robot, which is using the camera to decide visually where it should go, and then lengthen part of the robot, and then head towards a particular target. So the main challenge with this technique, while it does create for a relatively elegant robot deployment, it is not reversible. So once you turn, you cannot unturn. You could turn in another direction, but only after you continue to grow. And so this is a really challenging scenario in which to enable shared autonomy, in which to have a human in the loop in any way. Because the human cannot go back and change or correct mistakes that have already occurred in the past. This is not that unlike a steerable needle example I'll give towards the very end of the talk. And so it's not impossible to have a human in the loop, but it is very difficult to correct mistakes. And in this case, you may really want to only use this in scenarios where you know you can get it right the first time. And if that's the case, likely autonomy on its own without sharing with a human may be the right way to go. And yet I still have more ways to steer a robot, so there's still a couple more. The next one is a reversible technique. In this case, in a technique that Laura Blumenstein in my lab has been working on, we can route multiple tendon string actuators along this kind of robot, and it is a reversible process, unlike the one in the previous slide. So in this case, we are able to lengthen and retract. The challenge here is that the shape of the robot is only really fully determined when you fully retract the cable and kind of hit end stoppers. We're working on methods, which I'll mention a little bit later, where you did remove that limitation. But the nice thing is that you can get very complex shapes that are pre-planned into the robot, and depending on how and whether you pull the string or not, it may be in one configuration or another. And this particular example shown on this slide is actually using this technique in order to create an antenna for communications purposes, and switching the chirality, spinning one direction versus another direction of the helical antenna affects its polarization and the way in which it can be used for communication. So as you can imagine here, you clearly have multiple degrees of freedom. You have the growth degree of freedom, and you have the amount of string pull. And so what you could start to imagine is shared autonomy scenarios where those different degrees of freedom are divvied out to an autonomous system versus a human input. And in this case, because the shape is so complex, it's really hard to imagine how a human operator would fully control all the effective shapes and degrees of freedom of the final, or I guess description of the geometry of the final robot. And so it really makes sense that some aspects of this would be autonomous, where some which are easy to visualize and control for a human operator would be the aspects delegated to the human. And then the final way in which you can steer a growing robot, which is one that we've been as a most successful with to date and have implemented a human in the loop control, is to uniformly shorten one side, but this time not with the tendon method, but now with a reversible method with soft pouch actuators, as shown here. And so I'll just play these videos one more time on the right so that you can see how actuation of these pouches affects the steering of the robot, and simultaneously you can also grow. These videos that are shown here are actually still in the case of an autonomous system, but we'll see now that this can also be accomplished with human in the loop control. So I'm getting short on time, and I want to make sure there's time for questions. So I'll sort of skip through some of the details about exactly how this robot works, but sorry, the reference is a bit out of date. You can find this in a RAM paper, Robotics and Automation Magazine paper, which is also being presented here at ICRA, and that paper now exists. So we've deployed this as a full system, and we've shown that even children can teleoperate it. And one of the most exciting things was that my student Margaret Code, and in collaboration with simulations done with Professor Jihuan Ryu's group, has taken this robot to be used in an archaeological expedition. And I'm briefly going to show this video, hopefully with no sound, fix that, of the robot being deployed in the archaeological expedition. And I might see if I can skip ahead to portions where you can see the robot being teleoperated with a soft interface. So skip a little bit ahead to see if we can view the teleoperation component. And that jumping ahead does not seem to be working, but I'm happy to share these videos. There's actually a video that, here we go. This part of the video shows, if it decides to keep moving, Margaret teleoperating this system. And again, she's using a joystick, which is really mostly controlling the steering, but it also has a thumb movement to control the growth degree of freedom. And it's playing very slowly. Out here you can see teleoperation. Hopefully everyone can see that. But if you want to see this video in all its glory, I suggest you look at our Charm Lab YouTube channel, and I can throw a link to that in the Slack channel later so you can see much better videos. All right, so what are we doing with this now? We've implemented this into a soft growing manipulator, so it has less length, but the purpose is for it to hang from the ceiling and be used to pick up and move around objects similar to a more traditional robot manipulator. And a key aspect of it is a tip mount that includes a gripper. And that device development is primarily being done by Ming Luo. My PhD student, Brian Doe, and I'm going to rush through these now, has been looking at stiffness control of this type of robot, which will be very important for use as a soft manipulator and picking up loads. So he used layer jamming in order to control stiffness, which is another interesting question for how the human should be in the loop in shared autonomy. And Margaret Code has, working with Sanggu Jiang, has also worked on retraction without buckling. Well, while I've said that the robot can be retracted, that has been challenging in some scenarios. And so in a paper we've under review for IROS, we've been looking at retraction of these robots. Let's skip over our tip mount. And finally note, we've done some experiments which are being presented this week at ICRA 2020 by our postdoc Fabio Stroppa. It's also nominated for a Human Robot Interaction Best Paper Award, where we are not yet doing the shared autonomy component, but we are doing human-in-the-loop teleoperation in order to perform pick-and-place manipulation tasks. So really this hopefully throw out some interesting ideas about what should shared autonomy look like for human-robot interaction in these sort of soft robot scenarios. And just to compare this to a couple other related types of systems, I want to note our prior work in steerable needles. This comes from Anne Majewicz, who looked at shared autonomy in terms of targeting a steerable needle. And the steerable needle, although it doesn't grow from the tip, it does curve through tissue in a way that is somewhat akin to the steering of our soft-growing robot. And one of the things that she looked at was haptic feedback and essentially virtual fixtures to communicate the kinematic constraints of this novel type of steerable robot. And so we can take inspiration for shared autonomy and which degrees of freedom should be autonomous versus automatically controlled from this type of system. In this case, what Anne Majewicz decided to do was have the human control the dangerous degree of freedom, which is the growth. And the robot autonomously controls the other degrees of freedom. In addition, we've also looked at how haptic feedback can help steer humans, which are not exactly steerable robots, but interestingly, humans do tend to walk around in a kind of non-holonomic fashion. So we've also looked at how haptic feedback can guide people to reach targets. And you can see this diagram flipped on its side on the right looks a lot like the steerable needle one. And so we can also steer vine robots, we think, with these kinds of algorithms. And it may be very important to learn human responses to haptic cues. So as I close, I hope this gives you some food for thought in how we think about human interaction and shared autonomy with these interesting soft robots. And maybe some of the things that we can discuss, if there's not time very much for questions in the panel, are about what challenges are created by soft robots for shared autonomy and what advantages are there for soft robots when applying shared autonomy. And with that, I'll thank you for your attention. And if there's time, I'd be happy to take questions.
Thank you, Allison. It was very nice presentation. I mean, I really like this kind of idea of the growing robots. We have a couple of questions for you. So the first one is from IDSDT. And they say, where do you see this technology goes specifically in medical applications? And
Yeah.
also advancement of which technology benefits sorry, it was another question, sorry. And also advancement of which technology benefits more divine robot?
Yeah, that's a great question. So on the medical side, Elliot Hawks and also Tanya Morimoto have been exploring very much the medical applications of these soft-drawing robots. So from the perspective of just the mechanics of the robot, they're very advantageous for medicine because, as I mentioned, you don't have friction along the whole body. You can grow out the tip, and that allows you to change the target of the tip without having friction with respect to the environment, and this could prevent tissue damage. It is challenging to make these small in a small form factor, especially when you talk about, say, the size of the vasculature in the brain. That is extremely challenging. I think how we would handle shared autonomy in those scenarios is also very interesting. I mean, these are very safety critical medical applications, and it may be it would be quite a bit of time before any autonomous aspects were were enabled, and so maybe everything should be done using direct teleoperation. On the other hand, they are very constrained environments, and so you could argue that the robot will naturally, in this constrained environment, not require very special control. You will see you need to move it forward and backward. But you might also argue that you don't want to be pushing on these soft tissues, and the situational awareness and how you display the environment to the human operator is something that I think is an open question for integrating human control in the medical applications. Can you remind me the second part of the question?
Yeah, it was written also advancements of which technologies benefits more divine robot.
Right. So I definitely think that having better, I guess, thinner but very robust and flexible but not stretchable soft materials is important to make these vine robots very small. So I think materials development and identifying those best materials is important for future vine robots, especially in medical applications. I think also smart, flexible actuators that are very low profile either can be communicated with wirelessly or have very few wires is also really important for being able to both steer and sense. So whether it's actuators or sensors that are being mounted on along the whole length of the robot, having those soft, flexible sensors with very few wiring requirements would also greatly benefit the Vine robot.
Thank you. I guess that there is time for the final question. I take the last one. So
Okay.
how would you consider sensing with these kind of robots?
Yeah, sure. So for starters, there's all the types of sensing you would have with traditional robots. These could be cameras, whether it's eye in hand or remote. But I think the thing that's quite unique that would be useful for this type of robot is a sense of proprioception, especially because the robot can passively mechanically deform based on contacts with the environment. And sensors for that, I would say we don't have fully, we don't have great answers to what should be used. We looked at using optical fibers, which are probably going to be very appropriate, but they're also currently still very expensive. We've also looked at mounting curvature sensors at different locations around the robot, but that creates quite a bit of encumbrance and wiring, hence the earlier suggestion to find new sensors that reduce wiring. And then the robot itself can deploy novel sensors into unusual environments. For example, we are exploring burrows of the endangered California tiger salamander around Stanford University in holes in the ground. And we would like to measure temperature and humidity. And we would also like to track the motion of the robot, but getting signals through the ground has been challenging for using external kinds of sensors.
Thanks a lot. I mean, there are also other questions, but I guess that we are a bit late. I thank Allison again for her time and also for connecting with us from California. I guess that Serena may